Welcome back. This is Sinha. Last lecture, the outside kept pushing our oscillator around, and rhythm decided everything. Today, oscillators discover each other. Two pendulums will share one support, two masses will share one spring, and the swing you lend will come back. Hidden in that trade is one of the great ideas of physics, the normal mode, and by the end, it will be yours. Our story starts in 1665. The great clockmaker Huygens lay sick in bed, watching two pendulum clocks hang from the same wooden beam. However, he set them going. Within half an hour, their ticks locked in perfect step. He called it an odd sympathy and blamed the beam. He was right. The beam was passing tiny nudges between the clocks, tick by tick. Here is the modern version of his experiment. Two identical pendulums, one shared support and a whisper of coupling between them. Start the left one swinging and hold its partner still. The first swing shrinks stroke by stroke while the partner wakes and grows until the lender hangs completely quiet. Then the whole story runs backward and the borrowed swing comes home. Nobody touched anything, and yet the energy commutes back and forth in slow, hypnotic beats. Hidden inside the trade is a secret. There are exactly two special launches for this pair where nothing trades at all, where each pendulum keeps its swing forever. Every other launch, including ours, is secretly a mixture of those two frozen patterns. Find them, and the tangle unravels. Here is the plan. First, Newton for two coupled masses and the handshake term that ties their equations together. Second, the special motions, the normal modes, and the new coordinates that set them free. Third, beats and the physics of the borrowed swing. Fourth, the payoff, a swinging double pendulum, and the vibrating molecule behind the carbon dioxide laser. Back in the Universal Spring lecture, we parked a promise. A pair of masses chained by springs to one wall, beyond that day's tools. Today, we finish the job, upgraded for symmetry. Two equal masses each get a wall spring, stiffness K, and a middle spring joins them. Its stiffness carries its own Greek symbol, kappa, defined once on the slide, and a name, the coupling stiffness. That middle spring is the handshake. Watch the handshake work before we write it down. Hold the right mass fixed and push the left mass over. The middle spring squeezes and the captive right mass strains against your hand. Release it and it jumps. Whatever one mass does, the other feels immediately. Two objects, one shared piece of hardware, zero privacy. Now we write that down. Measure each mass from its own resting seat. x1 for the left mass, x2 for the right, positive to the right for both. The outer springs care only about their own mass. The middle string cares only about the gap, x2 minus x1. Stretch the gap and it pulls the masses together. Squeeze it and it pushes them apart. Newton for the left mass, term by term on the slide, its wall spring pulls it home, minus kx1. The handshake pulls it toward its neighbor, the coupling stiffness times the gap. Two forces, one acceleration and an equation that would be pure lecture. 7 except for one intruder. The neighbor's position, x2, is sitting inside the law of motion for mass 1. The right mass tells the mirror story, its own wall pull, plus the same handshake with the opposite sign because the middle spring tugs its two ends opposite ways. Now read the pair together. The equation for x1 contains x2. The equation for x2 contains x1. Each mass drags the other into every step it takes. That is coupling, written down. Here then is our quarry, framed on the slide. Two second-order laws, perfectly symmetric, each infected with the other's coordinate. Stare at the structure. The diagonal terms are lecture 7. The cross terms are new, and they are equal and opposite. Symmetric systems hand you symmetric equations. And symmetric equations, as we are about to see, nearly solve themselves. Watch. And still, this pair is genuine trouble. Every method we own solves one oscillator with one variable, and here neither equation stands alone. We are not missing a technique, we are missing a point of view. The masses are coupled. But maybe, just maybe, some combination of the masses is not. Hold that thought through one experiment, because the machine is about to reveal it. Before any algebra, let the rig speak. Launch both masses together, the same displacement to the same side, and release. Watch the middle spring. Its length never changes, so it might as well be welded shut. Each mass feels only its own wall spring, and the pair glides in perfect unison, one pure slow oscillation. Nothing trades, nothing tangles, forever. Now, the opposite launch, equal displacements toward each other. By symmetry, the midpoint never moves, and the middle spring works double duty, compressed and stretched from both ends at once. Each mass effectively feels its wall spring, plus a doubled handshake, so the vibration runs visibly faster. Again, the pattern holds its shape forever. A second frozen motion, quicker than the first. Any other launch buys the tangle. Start the left mass alone and watch the motion wander. Swings swell and shrink, energy migrates, and the pattern never repeats itself cleanly. It looks lawless. But hold the two special motions in your mind and look again. Gold and blue are both in there, running at their own rates, adding up, arguing. The ghost frames in gray make the case. Freeze snapshots of the tangle and compare them against the two pure patterns. Every frame of the mess is some amount of the slow unison motion plus some amount of the fast opposed one. The tangle contains nothing new. It is a mixture, and only a mixture, of the two shapes we just met. These two motions earn a name, the normal modes. In a normal mode, every part of the system oscillates at one shared frequency while the shape stays frozen. The symmetric mode, gold. The anti-symmetric mode, blue. Two masses, two modes, and the count is no accident. This is the claim we now prove: every possible motion is modes, mixed. Now the algebra, and it is almost embarrassingly short. Take the two Newton equations and add them. Watch the handshake terms. One is the pull on the left mass, the other its exact negative, and they annihilate. What survives is the law for the sum of the positions pulled home by K alone. The sum never feels the coupling at all. Now subtract the first equation from the second. This time the handshake terms reinforce instead of cancelling. The difference of the positions obeys its own clean law, pulled home by the wall spring, plus the handshake counted twice. Two coupled equations have become two free oscillators. We changed no physics, we only changed variables. Name the new variables. U is the sum and V is the difference, each divided by √2 for tidy bookkeeping, with V taken as x2 minus x1, a sign chosen for a picture soon to come. U oscillates at omega s, √k/m. V oscillates at omega a, built the same way from the stiffer combination on the slide. Two private clocks ticking independently. Stand back and look at what we hold. Two exact frequencies for the pair, earned in 4 lines, no guessing, no approximation. The slow clock belongs to unison, blind to the handshake. The fast clock belongs to opposition, which works the handshake twice per swing. Every launch this rig will ever see is built from these two numbers. Audit before trusting. Let the coupling go to 0, cutting the handshake. Both frequencies collapse to √k/m, and the two clocks tick as one, exactly the lone oscillator of Lecture 7. Strengthen the handshake instead, and only omega a climbs, because only the opposed motion ever works the middle spring. The symmetric mode never even notices it exists. And now look at what U and V really are. When the pair moves in the symmetric mode, V is frozen at 0 and only U moves. In the antisymmetric mode, U freezes and only V moves. The new coordinates are not clever bookkeeping. They are the amplitudes of the modes, one dial for each frozen shape, which begs for a picture, so here it is. Forget two masses on a line for a moment. Plot x1 against x2, and the whole system collapses to a single moving point in a plane. Run the Tangled launch, and the point traces this dense, looping weave, never quite closing, never repeating. Everything the two masses can do is in this one curve, drawn by one dot. Now, the turn. Rotate the whole picture by 45 degrees. The motion has not changed, only our point of view, and the weave falls apart. Along the new horizontal axis, the point simply oscillates, slow and steady, at omega s. Along the new vertical axis, it oscillates faster, at omega a on its own private clock. The new axes are u and v, and this is the truth of decoupling. Adding and subtracting the equations was never a trick. It was a rotation, turning our heads until the tangle splits into two independent songs. Whenever the algebra of modes feels dry, remember what it is doing. It is finding the angle from which the dance looks simple. So here is every motion the pair will ever perform. Take the gold mode with an amplitude and a starting phase of your choosing. Take the blue mode with its own pair. Add them, 4 dials in total, and a launch specifies exactly 4 numbers, 2 positions and 2 velocities. Any start you can dream up, some setting of the dials will match. Play with the dials and watch. Turn up gold alone and the pair glides in unison, the tangle gone. Blue alone, the fast opposed vibration. Mix a little of each, and the familiar wandering returns instantly. 4 dials span everything this system can ever do. Superposition is not a formula here, it is a mixing desk. Set the dials for the hook's launch, one mass displaced, everything else quiet. That start excites both modes at equal amplitude, half gold, half blue, starting in step. Mass 1 carries the two mode cosines added together, one ticking at omega s, the other at omega a. The slide unfolds that sum with a single trusted identity from trigonometry. The unfolded form says everything. A fast wobble at the average of the two frequencies, multiplied by a slow envelope that breathes at half their difference. At the start, the modes agree, and mass 1 swings hard. As omega a pulls ahead, agreement drifts toward cancellation, and mass 1 fades while its partner grows. Watch the envelope ride the actual motion on the slide. Every crossing of 0 is a moment when the lender stands still and the borrower owns everything. Then the modes drift back into step and the swing returns home. Huygens' sympathy, the playground trade, the whole hypnotic exchange. All of it is two cosines slipping slowly past each other. This is the gift of mode language. In mode coordinates, nothing ever trades. Each mode just hums at its own frequency forever. So, solve there, where the physics is simple, and translate back at the end. Two coupled questions became two free ones, plus an addition. That maneuver scales to guitar strings, buildings, and quantum fields, and today it is yours. Time to make the clock story quantitative. Our first problem. Two identical pendulums hang from one beam, tied by a weak spring whose stiffness is just 5% of gravity's. Start the left pendulum swinging, the right one dead still. Both modes wake at once, nearly equal in strength, and their two frequencies sit painfully close together. That tiny gap is about to run the show. First, translate. For small swings, each pendulum is an oscillator with gravity for its spring. Omega squared equals G over L. The weak spring between the bobs is the handshake, playing exactly the coupling's role. So the whole theory carries over, the two modes and the gap between them, set by the coupling. Same mathematics, new costume, first of two today. Call the gap delta omega, the difference of the two mode frequencies. Weak coupling makes it small, about 5% of the base frequency in our rig, and the envelope breathes slowly. The whole trade, lender to borrower and back, is choreographed by nothing but this one small number. Small gap, long story. How long until the swing is almost fully lent? The envelope hits zero when the two modes drift half a cycle apart, and that takes time. Pi over delta omega. In our rig, that is about 10 full swings, and the weaker the handshake, the longer the loan runs. Want a faster trade? Stiffen the coupling. Delta omega grows in step, and the gossip speeds up. Follow the energy books while it happens. Live bars under the pendulums track each one's share, and the arrow between them points from lender to borrower. The flow is not steady. It is fastest midway through the trade, when both pendulums swing with equal vigor, and it slows to nothing at the moment of complete transfer. Watch that moment closely. At time, pi over delta omega, the books balance out to a striking degree. More than 99.9% of the energy has crossed to the borrower. The lender keeps less than a tenth of 1% and hangs, to the eye, perfectly still, robbed blind by a spring it can barely feel. Then, patiently, the theft reverses. This is the physics Huygens was staring at, energy commuting across a shared support. His full story had one extra ingredient, the clockwork that kept each pendulum fed, which is why his pair locked in step instead of trading forever. But the messenger is the same. A weak coupling, given patience, moves everything. The next time something wobbles in sympathy, you will know exactly who is whispering. Second problem, and a change of costume. Hang one pendulum from the bob of another, equal masses, equal lengths, and keep every swing small. Not a spring in sight. If the mode idea is honest physics and not a spring trick, it must survive this. Two angles set the shape. Theta 1 for the upper rod, theta 2 for the lower, and their two rates complete the state. Newton on the upper bob, and the first surprise is the tension above it. That string holds the whole chain, both bobs, so for small swings its pull is twice mg. The lower string pulls back with a single mg tilted by the lower angle. Write the sideways components and divide by ml. The 2 appears honestly, twice the gravity rate on theta 1. The lower bob hangs from a support that itself swings. Its sideways position is the upper displacement plus its own, L theta 1 plus L theta 2, so differentiating twice stacks the two accelerations. Gravity pulls it back through the lower string alone. Divide by m, L, and the mirror equation lands, the summed accelerations against the lower angle. There is our familiar shape in a new costume. Two equations, each dragging the other's angle, the coupling now carried by tension instead of a middle spring. No approximation beyond small swings was needed, and no spring anywhere. The mode machinery we built is about to meet its first test away from home. Hunt the modes exactly as before, a frozen shape at one shared frequency. Assume both angles swing as cosines with amplitudes, A1 and A2, and feed the guess through both equations. Every derivative brings down minus omega squared, and the time factors cancel. What remains is two conditions relating the two amplitudes. Two conditions, one ratio. Solve each for A2 over A1 and demand the same answer from both. Cross-multiplying clears the fractions, and a single condition on omega squared remains. A quadratic worked line by line on the slide. 2 degrees of freedom went in. A quadratic with exactly 2 roots comes out. The frequencies land as omega squared equals 2 minus root 2 or 2 plus root 2 in units of G over L. Odd-looking numbers, honest pictures. The slow mode leans together, both bobs sweeping the same way, the chain moving like one long soft pendulum. The fast mode is the counter whip, bobs opposed, the elbow snapping side to side. Now the audit. A lone pendulum of this length would swing at root G over L, and that number sits cleanly between our two answers. The leaning mode is slower, the chain acts longer than its parts. The whip is faster, the tug of war stiffens it. Coupling split one frequency into two, one below, one above. Molecules are about to do exactly the same. The final problem is a molecule. Carbon dioxide is 3 masses on a line, oxygen, carbon, oxygen, joined by 2 identical bonds that behave like stiff springs with nothing anchoring the ends. 3 masses along the line should mean 3 modes along the line. We will find all 3, and one of them runs the most common industrial laser on Earth. The recipe scales without complaint. Write Newton for each of the 3 atoms. Assume a frozen shape at one shared frequency and demand consistency. 3 coordinates deliver 3 allowed motions along the line, each with its own character. We will read them straight off the molecule itself, one at a time, and each one tells a story. The first mode arrives with frequency 0, and it is telling the truth. Slide all 3 atoms together by the same amount. Neither bond stretches, nothing pulls back, and there is no oscillation at all. This is the free molecule drifting through space. Translation: wearing a mode's costume. Free ends always hide one of these, and now you will never be surprised by it. The second mode is the symmetric stretch. Both oxygens swing outward and back in mirror image, while the carbon, held by symmetry, sits perfectly still. Each oxygen rides its own bond alone, so omega squared is K over MO, the oxygen mass carrying everything. The heaviest work in the molecule, and the carbon does none of it. Symmetry decides who works. The third mode is the anti-symmetric stretch. Both oxygens lunge one way, while the carbon rocks the other, keeping the center of mass nailed in place. Because the light carbon must counter 2 oxygens, the bonds work harder and the frequency jumps well above the symmetric stretch. The slide carries the exact result, with the carbon's mass now firmly in the game. That fast asymmetric wobble is a celebrity. In a discharge tube, energy pools in this mode, filling the upper rung of a ladder. The molecule then steps down to the symmetric stretch, paying out the difference between the 2 modes as infrared light. That payout is the carbon dioxide laser, the workhorse that cuts steel. Both of our modes working one machine. One honest boundary before we celebrate. Our 2-spring model puts the stretch frequencies in a ratio near 1.9. The real molecule's infrared lines, quoted on the slide, sit at 1.69. The gap is physics we deliberately left out, the bending motions and the softness of real bonds. The model earns the pattern. The decimals belong to deeper theory. And now, one look over the fence. Real systems rarely share a mass. Make the left mass heavy, the right one light, and let the springs differ too. Add the equations now, and nothing cancels. The handshake still balances, but the accelerations no longer share a mass. The trick that carried this lecture has hit its honest limit. The rescue is bookkeeping, not new physics. Collect the masses into one grid, the stiffnesses into another, and the pair of laws becomes a single sentence. The mass grid times the accelerations equals minus the stiffness grid times the positions. Watch the four stiffness entries take their seats. Every coupled network in physics fits this one sentence. Hunt modes the same way, a frozen shape at one shared frequency. Professionals write the guess as an exponential e to the I omega t, the cosine in compact dress borrowed for a moment. Feed it through and the search becomes a classic. Find the special shapes these grids leave unturned. One polynomial, n roots, n modes, always. And the picture survives. Our 45-degree turn was the equal mass special case. In general, the axes still rotate, just by their own angle, and the mode shapes slant, unequal arrows on unequal masses. The full machinery is called eigenvalue algebra, a story for a later course. Today you have seen its face, and it looked familiar. For the last picture of the day, scale the idea up. 5 identical beads on a taut line, each coupled to its neighbors, walls at both ends. 5 masses, so the count demands 5 modes, 5 frozen shapes, each humming at its own pitch. Here they come, one by one, and their shapes are anything but random. Look at the envelopes threading the beads. The slowest mode arches once, one smooth bump. The next crosses 0 once, the third twice, on to the fastest zigzag, and the pitch climbs with every added wrinkle. And these shapes are not roughly familiar, they are exact. Thread a smooth sine curve through any mode and every bead sits precisely on it, the frequencies following one clean formula on the slide. Now let the bead count grow without limit. 1,000,000 beads on a line is a guitar string, and its modes are the harmonics musicians have tuned by ear for 3,000 years. The fundamental is our single arch. The overtones are our wrinkles. Every solid, every drumhead, every molecule speaks the same language of modes. That was the recap's promise. Paid. And when the beads blur into a true continuum, the modes join hands, and something new is born, the traveling wave. That story belongs to another course, and it starts exactly here. For hours, the tour is complete. From 2 clocks on a beam to the vocabulary of every vibration in nature, the normal modes run it all. 3 habits to carry out of today. First, find the special starts. Before wrestling any coupled system, ask which launches keep their shape forever. Those are the normal modes they never trade, and counting them is free. Count the independent ways the system can move, its degrees of freedom, and you have counted the modes before any algebra. Second, decouple by rotating coordinates. The add and subtract trick was a 45-degree turn in disguise, finding the directions along which the physics never mixes. When 2 equations drag each other's variables, stop grinding and start hunting for the combinations that stand alone. They exist, and they are waiting. Third, near a stable rest point, every wobble is a chord. Small motion is modes played together, each at its own frequency and volume, and beats, trades, and tangles are just interference between the notes. So, solve in mode language where nothing ever mixes and translate back at the end. The hardest coupled dance in physics is sheet music, once you know the notes. Next lecture, a new arc begins, energy. We have ridden force a long way, so now we change currency entirely. Work, potential landscapes, and the valleys that shape emotion before it even starts. And an old debt comes due. 2 lectures ago, the quality factor Q promised us an energy face. Lecture 10 pays it in full. Bring your curiosity. That wraps up this lecture. This is Amit Sinha. Thanks for watching the Sinha Foundation channel. See you in the next one.